Hello. I guess we should get started. Like we have like 120 slides and no. Well, I'm going to talk about something called XDP-hints. It's been talked about before, but I want to try to use the BTF, which is called the BPF Type Format to do some interesting stuff. But first, we need to have a reminder. I guess everybody knows what BPF is today. It's been around for, is it 7 or 8 years now? Uh, the website ebpf.io still says it's a revolutionary technology. It's been around for a while. We can run sandbox programs in the Linux kernel without changing the kernel source or loading any kernel module. So all of a sudden we can runtime extend the kernel. That's basically what it's about. Brendan Gregg says that BPF is no longer an acronym. It's actually a technology name now. And the old BPF, the old Berkeley packet filter, was just a way to get it into the kernel, like a kind of a sneaky way to get it in, because the instruction set today is like almost like a full ISA instruction set, right? But the whole idea is that the rate of innovation in the operating system, as we all know, as kernel developers, are traditionally very slow. So the promise from BPF is to radically increase this innovation and also do things that were not possible at the OS level before we got this technology. So this is, as always, good with cartoons, right? So we have our application developer up here, which wants a new feature that requires some kernel change. So he goes to his friendly kernel developers. They're always friendly, right? Please add this new feature to the kernel. And he goes, yeah, sure. Give me a year to convince the entire community that this is good for everyone, right? That shouldn't be a problem, right? He actually completes 1 year later. I'm done. Upstreaming in the kernel support. This is great. I'm going back to the people who requested it, but I needed my distro. And then 5 years later, we have adoption in the distro. And then 5 years later, the application developers, well, my requirements have actually changed. So that's a pretty sad story, right? So instead, we have a eBPF developer over here who wants the same feature, but he sees, oh, the kernel cannot do this today, so let's quickly solve this with BPF. And a couple of days later, he can implement it and release it in the project, and the user is happy, and he doesn't even have to reboot his machine. So that's the happy cartoon story. Another reminder slide is that what XDP is, because that's what I'm talking about and sort of what I invented. It's also been around for a while now. So it is, the slide used to say new programmable layer in front, now it's just a programmable layer in front of the traditional network stack. So where we can read and modify and drop and redirect and pass to the normal network stack, these frames that are coming in. For layer 3 and the layer 2 use cases, we are seeing a 10 times performance increase because we avoid taking a lot of the cost and overheads that are usually associated with allocating the SKB buffer, which is the metadata structure, and clearing that memory and and these kind of things. The other thing that makes XDP faster is bulking, but the way we implement it is it's adaptive bulking, so we don't just do bulking for the sake of bulking or waiting. We only do bulking when there's actually frames ready in the received descriptor ring. And what you get is very early access to the frame just after the DMA sync. And part of the trick to get these higher speeds is that we can skip large part of the kernel code. And the way we export, even though we don't have any SKB at this very, very early stage, we can still look up in the route table, for example. We have BPF helpers. We can actually, we just added, we can look up in the connection tracking table. And all these things we are extending so we can pick and choose what kind of features I want to use from the regular network stack at this earlier stage. That means, in principle, that we can skip a large part of code, so we don't execute that. That's the fastest, most efficient optimization to not run the code. But there's one pitfall that this talk is about, that we lost access to these traditional hardware offloads, like, for example, the receive hash and checksumming. So what are these traditional hardware offload hints that we lost, that I'm trying to bring back? So the hardware provides some offload hints in the descriptors. And these are descriptors for describing receive and transmit. And today the network stack will take these hints and put them into our SKB metadata structure to store this information. And that's not available at the XDP level. So we have the receive descriptors, we have the traditional receive checksumming, we have the receive hash, we have also receive timestamping, but not for all frames, like mostly for like PTP frames, for instance, and that. We also have the VLAN can be offloaded. On the transmit side, we can ask the hardware to perform some actions for us. The most common one is asking for the hardware to do a checksum for us. We can also put in the VLAN tag without having to put it into the packet header. We can just put it into the descriptor, and the hardware will take care of that. The more advanced use cases is getting the transmit timestamp. How do you do that? How it actually does it is you ask the hardware that I want to know when this packet was transmitted. And the kernel has a completion, DMA transmit completion routine, updating, reclaiming buffers from the transmit ring. And at that point in time, the hardware would have been written into the descriptor there, the timestamp, and you can extract the timestamp there and report it back. For example, TCP dump is one user of that facility. Another advanced thing that we've had customers wanting is the launch time. So you can ask the hardware to transmit the packets at a specific point in time in the future. That's a quite cool feature. So what are these XDP hints that this talk is circling about? So I cannot claim I sort of invented that, because it dates back to 2017, where Intel presented this idea to let XDP have access to these hardware offload hints. So the basic idea is we extract from the descriptor I just described, and somehow we store the information in what we call the XDP metadata area, which is located just before the frame. And the XDP metadata area has been available since like 2017. You can already use it today from a BPF program in itself. The space is limited, and I want to increase it a bit to be one cache line. But I believe the main reason that this XDP hints were stalled was that we couldn't agree on a layout for how we should use this metadata area. Everybody wanted their bits in the same place, right? So I'm going to talk about something called BTF, which was not ready at the time, but I'm going to teach you a little bit about what is available today. And it's actually a quite cool kernel feature if you don't know it. So my proposal is to solve it by having the area described by BTF. And each NIC driver, I want the flexibility that the NIC driver can choose the BTF layout. And I also have this slightly challenging requirements that I want to allow the driver to have per packet to change the layout, a meaning of the structure. For example, with the timestamping, we don't want to timestamp all the packets, That would also be too expensive for the hardware. But in some use cases, we want to have that. So the open question is will BPF be a good fit for this use case? And that would be a struggle upstream. I'll explain some of the technical details of BTF if you don't know what it is. There's a pretty cool feature. The kernel is basically self-describing the types in the kernel. So it's a compact type format based on the compiler's dwarf debugging information that gets actually compressed down because it's a compact format. So the entire dwarf data with like 124 megabytes was in one example for a blog post, and that was compressed down to 1.5 megabytes. And that means we can actually include that in the kernel image, and that's what we are doing today. And it is exported as a file you can have access to here. And I put a command line down here that you can actually run today, and think you can get automatically generated a header include file that describes all the types on the running kernel you're on. It's a pretty cool feature that the kernel has become self-describing. It's mostly used for tracing, when you want to trace something, and the relocation, I think I have a little bit slide how the relocation works. So there are actually more components than just the BTF. So we also have something called core-re for compile once, run everywhere, and we also have a component, libbpf, that does things. Again, Andre, he created a really good blog post where he explains all the bits of the puzzle. So the basic idea is that we want these BPF elf objects files to be portable across different kernels. So if a struct layout changes, we can still run the same program. We will just adapt the offsets the BPF program uses to get the right member in a struct. So the BPF loader, the libbpf, combines the different pieces. So we can tailor it to run a specific kernel, and it looks, the LLVM compiler have put these BPF relocations in. Relocations is a normal thing for ELF files, but we added something extra so we can match on more things. And then, like I said, we update the necessary, the libbpf updates the necessary offsets and the relocation of accessing members in structs. That means that the kernel can be free to change, or the kernel developers can be free to change the layout of structs, and the tracing tools will still work. And I intend to exploit this for networking. So a code example. Is there some? Can this? No. Oh. There was no laser pointers, I can assume. No. So we can actually define a struct over here, which only a few members. It's a little bit difficult to see on the slide, but there's tree underscore local, the sk underscore buff, and I only define one element I'm interested in the hash, and I put this strange attribute preserve access index. In my BPF, this is a BPF program. Then I can access, attach the probe, and the probe, I'll give it actually the type. The BTF or the libbpf will, oh, thank you. Which one? Okay, yeah. Great. So we actually give it this type. libbpf will actually remove this part, and it will figure out with the preserve access index how I can access different things. This is a macro helper that I want to read it into to the 32-bit variable from the XDP-hints from the hash. So it's the same as dereferencing the pointer, and I get that in. I also added that you can actually ask for, there's some, I come more into that later, that you can get the type or the type ID, which you can also dump from user space and see. You can ask for that in the BPF program itself, so it can know its own ID. I'm going to use that later for some tricks. And here I'm just printing it out via the trace buffer. So we have these type IDs, and they are basically referring to each other. The IDs are generated basically when the kernel sort of boots it, but it's also could be determined from the VM Linux file because it's loaded in a specific order. Yeah, and so the 0 is not a valid ID, and they start from 1. And we have the tool to dump them, so you can play with this from user space and actually see it. There's a number of files, as I mentioned before, in sys kernel BTF. So there's for the main files, the VM Linux, it contains all the types that are compiled into the kernel. And then there's also module files. These ID numbers start from the last ID of the VM Linux. That's because the module files themselves can refer to the IDs from the VM Linux BTF. But that also means that our module starts will have, they are sort of not unique. The VM Linux IDs are unique, but the module files are not really unique. User space in itself can also have BTF sections, and you can then, they will get matched, either if you have the preserved access index, they will get matched by libbpf against the kernel, and then do the offset adjustments. That's one way that we use the BPF programs, BTF sections in the ELF file, and but we can also have local BTF information, and that also starts at 1, the counting. And I'm going to use a trick where we can, before we had an example where this was kernel, and now this is local. I can also ask my own ID from the runtime. So back to the XDP-hints and this strange metadata area. The metadata area have some sort of a little bit strange properties. It starts at the packet header start, and then it goes backwards. It's only 32 bytes and must be 4-byte aligned. And you can grow or expand or shrink the area runtime. So if you want to use it in that's how we do it today. We can call it a BPF helper, called the adjust meta, and we can grow this area and put different stuff in there. And then the verifier will do the boundary checks, or we require that you do the boundary checks on the metadata area, just as you have to do today for accessing the data area, for gaining direct memory access to the data area in packets. You can get a little bit surprised because of this grows backwards, and then the C compiler thinks that you grow forward, and then it'll do padding in the end to do like nice alignment. So sometimes you have to use the attribute packed as a trick. So what expected users do we have of this XDP-hints? So we have the BPF programs themselves. That's the first obvious user. And you can actually also access this from the TC hook. So it's later, today you can expand it, and then the TC hook, you can put information from the XDP program, and then the TC hook can read this information and the TC hook happens when the SKB is allocated. Not a lot of people realize this, so I just want to mention it. One of my use cases is that I want when we do the XDP to SKB conversion, we both have in VHH and CPU map. We want to not lose these traditional hardware floats and get them carried over. And we have chained BPF programs that communicate state, and we have AF XDP that can consume BTF information in user space and decode this area. And I have a code for that because people complained that it was difficult, and it's not. Just show me the code. So my motivation for the XDP to SKB conversion is that it's sort of a moonshot that I want drivers without any SKB knowledge. It should simplify the drivers a lot. And we can avoid taking the socket overhead from the SKB at the driver level. And my next moonshot is then you can then speed up general Linux bridging and routing. And that would be great. So there's also some hardware motivation because the end goal is actually that the hardware should produce these XDP-hints. It's just next to the DMA area that is the hardware like to align it on a cache line from the above, but we can easily have the hardware write the metadata area and the XDP-hints, and then we have to consider the engineness and stuff like that. But fortunately, we can just add that later when the hardware appears, because we have the flexibility of the driver can redefine the layout. So exploring different solutions. So these ideas are not fully formed, and I will likely get hit on upstream. So the first one is internally focused, where we extend the XDP buff and the XDP frame with the ID or pointer directly to the BTF. And then we can extend it to have a context, so you can read you can read it from the context object from the BPF, the ID. The problem is that AFXDP cannot read this, and it's also unknown what should the semantics be for chain programs when they update or want to update this BTF ID. So that use case with the chain programs is sort of undefined what should be the right approach. Internally, it's good because we can store a pointer directly. We don't have any lookups. We do need to handle some lifetime stuff. It helps the XDP to SKB conversion. So that's sort of nice. But if we store direct pointer, how do we handle the different layouts if the package layout changes a lot, or once we want to change that? And the kernel sees a pointer, and should we have several pointers to different layouts? So that's also an unknown I was discussing with Magnus yesterday. And if we log it down, there's only one layout per packet, which is kind of not so flexible. We could even store it in some area called the XDP receive queue info, but that's just a detail. The solution B is decoupling it and just using the BTF ID in the metadata area. I know I always claim it's Björn, I think he's here somewhere, that invented that on the mailing list. So we simply store the BTF ID as the last member because it goes backwards. And then in AFXDP, what we do is as it's 32-bit, we do minus 4 bytes. And then we look at the ID there, and then we know the layout of the structure. Given the ID, we actually also know the size of the structure, because we can ahead of time look up all the IDs we are expecting, and then be able to get it that way. And that, I think Björn is up there. The idea was also he's the AFXDP maintainer, and the idea is that we don't take up any option fields. We would need one bit in the descriptor for AFXDP, saying that this frame contains BTF information, and then we know we have to look at the first or minus 4 bytes. we might need three bits because there's it can either the ID could come from VM Linux, it can come from module, or it can come from the local ID that I showed I could extract before. So that's a little bit unknown. I'll see if Bjørn will give me three bits. Bjørn and Magnus. But the decoupling via the BTF ID also becomes sort of the struct's version number, and you can then like extend the struct and know from user space how this is sort of connected. It's kind of easy to handle layout per packet, as the BPF program and the AFXDP program can multiplex on these IDs, and then it can say I know these upfront, and then that's at least how I implemented my code. That it's on setup time it decodes the BTF information, so it doesn't have to do it runtime, and just knows the IDs, and then it can go figure runtime, just do a lookup on the ID, and then know the struct's offsets. If you only have the ID coming in, then the in-kernel XDP to SKB conversion is kind of harder, because how can we trust this ID? So one option is we add a new hook at that point where we create the SKBs from XDP frame pointers, and then we do the same, that we have to write a BPF program that populates the fields based on the BTF information. That's also one option. Solving BPF with BPF is sort of a thing that upstream likes, and I guess the rabbit hole is deep. Solution 4 is the sort of the combined solution. We still place the BTF ID inside the metadata as a last member, but we consider it a cached version of what's on the kernel side. We store a pointer to the BTF. We still have to handle the lifetime handling inside the kernel. That's not so nice. And it also works easier with the SKB conversion, because we can then check if the ID matches the ID that the kernel pointer has, and then we can trust the layout and have C program access this. The chain programs also works because the ID, the last member, becomes the communication channel. I don't know how we should communicate where the origin of the BTF is, if it's the VM Linux module or local. We could extend it. Magnus suggested that we could just have a bigger BTF ID or something before the BTF ID with a type. So how do we solve exporting these, like if the driver implements a number of these layouts, how do we export it to user space? You need to create a new API, as I discussed with Magnus yesterday, or could we just use the files that are available? Like we have the syskernel BTF. We could just say the module name here, and then extract that, and we can just have a naming convention. For example, they should be called XDP-hints, and then underscore something. And then we can sort of export the layouts that way. Then we don't need any new UAPI. I have to switch this one. One proposal to like export how, or to let a driver know via this interface, how can we say what structs or BTF layouts it's supporting? We could just have a union called XDP-hints _union, and we can then add the structs, and that means that the driver may use this BTF layout. So that's why we can have several ones of them. As I explained before, automatically everything gets the BTF ID. So even ints have a BTF ID. So all the substructs will have the BTF ID, so you can just scan, find the union, walk that union, and check all the top-level structs defined in that. That will be the list of BTF IDs that this driver exports. One complication is that it grows backwards. So if we want this union to actually match the memory layout instead of just being a container for user space to list, then we need to do sort of padding on top whenever some struct is larger than the other, right? So, and it quickly gets ugly in C code. It would maybe some driver developers would prefer it to have this way because it would be easier to have one type. It's also a little bit, we talked about Rust yesterday, with all the type safety. You can cheat and have this union, have the right memory layout, and then you just pass a pointer to this union, and then you just know that the hardware has enabled these features, so there's this layout, and then I know I can write in here. And then, so that's not very type safe. Definitely have to put unsafe around that. Another sort of compromise is we could have like a partly define some UAPI or KPI that we could, in the kernel, in the VM Linux BTF world, we could define something called XDP-hints common. It would be exported via the BTF header file, which is UAPI, and we could also have some defined because it's easier to have some flags if we want to. Likely, as the space is limited, we likely need to have some flags and some bits defining what parts of the current struct has been filled out by the driver. So it could be a compromise to have some of them here, and then drivers could include this common struct as a member of their driver when they want to extend it. Of course, they have to extend it on top, as we explained, it goes backwards. And then we could have like one bit in a flag that indicates, well, this layout, the bottom part of the layout is actually compatible with this common struct. And then we could easily have like the kernel trust that this is the common struct, and the information there, I can use that to populate when, for example, creating the SKB or other things. But it does go against like the fully dynamic BTF world that we can just create new layouts as every driver see fits. But sometimes it's also good to standardize a little bit. So. Yeah. I think I mentioned this before. I see it as a communication channel that we have created. And this actually already works today with chain programs and also BPF programs sending information to user space via the AFXDB socket. And I actually implemented this as you can find my slides and links to this. So we can have transfer information from the XP program to the AFXDB program, and I did this via BTF. And it's here. And the use case was that in the wind turbine at Vestas, they have these things for real time. They have something time-triggered Ethernet system where they have to send to a specific time, and they also get inputs from a master clock where they have to get high-precision timestamping. So what we did was, at the XDP level, we added the receive timestamp. Then the real-time application didn't have to like be pulling on the NIC to get a high-precision timestamp, because it was only they were only interested in getting high precision for the timestamp packet to to synchronize the clock when they have to send. All the other packets on the receive side, they could handle a little bit later. That was not real-time critical. It was pretty annoying. They would have to spin one CPU to get high precision timestamps. We resolved that with XDP. We put the XDP program, and we have the hardware. No, not we have the software receive timestamping. They wanted the hardware stuff. That's sort of what I'm trying to extend now, that we can get that. So that's what's actually quite nice. They have copy-pasted my code from there into their code, and it says it will take a year before it hits the wind turbines, but that's production, I guess. So what I did was I used the local BTF stuff in the ELF object. Then I didn't need to do any kernel extensions. And then I got the local ID this way. And then user space would then decode the BTF format and the available BTF IDs in C code in user space, and then we could extract the offsets and size for the name struct members that we're interested in. And that turned out to be quite nice. And we also had we had to debug something. We just added, what CPU was this coming on, and then we just added that to the BPF program, extended our BTF, and we could then debug this, and we didn't have to care about, oh no, the layout is changed, now we have to update the program because we just extracted the offsets dynamically. So that was quite nice. And I think that's the end of the show, because we have a lot of other people like to talk. So questions? Everybody convinced this is a good idea.
There will be another question session later.
Yeah.
We also can maybe handle the discussion when we wrap up all the XDP things. I think.
Yeah, that's probably better.